Now, in our last video, we derived the vector acceleration, like we got the expression in a way, and then we got to this point where we said this whole thing, we call it our AR, then UR, plus this whole thing as our R theta, A theta, acceleration theta, U theta. Now, if there's this way that you can use to remember this expression as expression without having to write it this big. I'll take it down one by one. So I have AR is equal to d square R over dt square minus R d theta over dt square. You know, this is R, so this is d square R, so it is derived twice. Yeah, so since it's been derived like 2 times, I can just simply use R, because it's R that is the boss here. So this R, then, to show that it has been derived twice, okay, then minus R, okay, and then theta it has been derived once because it's d theta su dt over dt. So it's d theta over dt, and so it has been derived once. So I'll just have 1 to show that it has been derived once, and then raised to the power of 2, that is this. Yeah, so finally my ARUR will be this UR. Cool, right? And then for A theta, we'll do the same thing. For A theta, we have 2dr over dt, d theta over dt plus rd square theta over dt square, and u theta. So, okay, so since I did that there, I should do it here as well. So now what do we have? We do the same thing again. You can actually pause the video and then try out what it might be. Okay, so this is 2. Yes, it stays. And then the r dt has been derived once, so it's going to be r and then 1. Then d theta over dt has been derived once also, so it's going to be theta this. Then plus, okay, r, the same r comes up, and then d square theta over dt square, meaning theta has been derived twice, so we'll have theta comes out like that. So this is a short expression for it, so we just get u theta. So at the end of the day, what do we have as our composants for vector acceleration? We have this. For vector acceleration, we have this, just like how we did for the other one. So we have AR is this or this. If you can remember this, okay, but you can also work it like this as well. So this is R minus R theta au carré, and of course we call this the composant radial. So they will ask you in your TD to calculate the composant radial de l'accélération. It's this. Yep, you just use this expression and then maneuver your way through. And this is 2r theta plus r theta theta. Yes, so this is the composant transversal. So yeah, these are like the basic things you should know. So we're going to do like rappel summary. At the beginning, I started with telling us that when coordonnée polaire is called, the two things that should come to your mind is we're working with r, we're working with theta. And the rayon polaire, that is r dot t, is om dot t. It's this. Then the rayon polaire of theta t is ox om. Reason: we have om, we use this, and we said we have om, o à l'origine, m, and then we said r, function of t, is equal to absolute value of om to the sa, and this is our r. It's placed here. Same applies to theta t. Theta t is ox om. It's the angle power ox and om. Power ox and om. So we have it here, here. And what other thing did we remind ourselves of? We said that they can of course vary with time, because it's in function of time. So it can vary with time, of course. At t equal to 0, so you get, and then t equal to 0, sorry. And then the rayon L and the angle theta, we call the r the rayon, we call the theta angle theta. Yes. And then what other thing did we mention? We said that we have two vector unit there. We have the ur and the u theta, and then the ur is in the direction of om. You can see it, it's in the direction of om. And then u theta is gotten by doing the rotation of ur, by rotating ur to create an angle p pseudo, an angle pi over 2, which is the angle 90, to create an angle pi over 2, which is our u theta. Yes, so that explains this diagram. And then what else did we do? We derived our ur and our u theta, and we said dur over dt, it will give us d theta over dt u theta, and then du theta over dt will give us d theta over dt ur. Okay, I was looking at this. Okay, this is it. Sorry. So du theta over dt and minus d theta over dt ur. Vector. Please do not forget that. And then from there we went to what's the relationship between the coordinate Cartesian and the coordinate polaire. We gave this diagram. We have a coordinate Cartesian x, y, and x and y, and then our om, and then r. Remember this. So r, and then our angle theta, the ox om. Okay, and we said the relationship is x is equal to r cosinus theta and y is equal to r sinus theta. And then we now went like the vector position, the vector vitesse, the vector acceleration. So from the vector position, I'm not good at that. For the vector position, we have om is ru r, yes, and then our vector of vitesse, after all this, we got this. We said the r dt is vr, and then united r d theta over dt is v theta, u theta, remember this is theta, and then u theta. And so what's the composant of the velocity? Composant of velocity is divided into two: composant radial, composant transversal of the velocity, and it is vr equal to the r over dt and v theta equal to r d theta over dt. I said like maybe in subsequent videos, might not be the next video, I'll show you how this expression is really like how we have it here. Now the vector acceleration, we applied the same thing. Remember we got this v from dom by using the velocity, by using the position, and then we said when you go from position to velocity, you derive position, velocity to acceleration, you derive. So we have dom, we use this expression, and then same thing applies here. Since velocity from after velocity, acceleration, so acceleration vector, don't forget this vector, it's dv over dt. And what was our v here? I said it was dr over dt ur plus r d theta over dt u theta. And then after the expression, I did not say it from this point is this, I'm just saying after breaking down this expression, you arrive at this. And we said this, we called it ar ur, and then this we called it r theta, this whole expression r theta, and then u theta vector. And then we got the second way of breaking this down so that it won't be like so large this way, so you can break it down like this. And we did the same thing for r theta u theta, and we got this as well. And then the composant of the acceleration is ar do ar r, this we call it the composant radial de l'accélération, and r theta composant transversal de l'accélération. So I hope I've been able to at least give you like a hint of how the coordonnée polaire works on that cinematic dipole material. Thank you. In our next video, we'll actually be trying out one question from our TD, and so that we'll be more like sure that this is how it works. So see you in the next video. Thank you.